In this module, we will be discussing agglomerative hierarchical clustering. As you will recall, clustering methods are broadly divided into two distinct methods. One is the hierarchical clustering methods and the other is the partitioning methods. Of course, there is a third method which is the overlapping clusters, but these are by nature fuzzy in nature and hence very often are not very seriously looked into because they don't give you distinct clusters. Now, as you again recall that hierarchical clustering is done when the observations are distinct and we are interested in the individuals themselves, whereas partitioning is done when the observations by themselves are not distinct and we are not interested in the individuals, but we are more interested in the groups that they form. Now again, hierarchical clustering can be of two types. It can either be formed in an agglomerative manner where we start with n clusters and end up with a single cluster at the very top, or it can be the divisive method where we start with a single large cluster and keep dividing this till we get down to n different clusters. So today we will be discussing the hierarchical agglomerative technique. In agglomerative hierarchical clustering, we start with n distinct clusters at the bottom of the tree or the dendrogram. We need to pre-decide on the distance measure that we are going to use. This distance measure obviously is the distance between the member or the observations. We also need to decide on which linkage to use to measure the cluster distances. Once having decided on these two, we merge the closest clusters one at a time till all clusters merge into a single cluster of n members at the very top of the tree. This is briefly what we do in agglomerative hierarchical clustering. So we need to first look at the distances. We have looked at some of the distance measures in the previous modules. Recapitulating those, remember that when we have all continuous variables, we can use the city block distance, which is the straight line distance in the perpendicular direction among different observations. We can use the Euclidean distance, which is the shortest distance between two of the observations. We can use the Minkowski's norm measure, a special case of which is the supremum norm. We can use the Mahalanobis distance. The speciality of the Mahalanobis distance is that it is a normed measure. The measure is actually divided by the variances so that it lies within a certain interval. We can also look at Gauer's measure. An alternative measure is the Bray-Curtis measure, and finally the Lance and Williams measure. The Mahalanobis, Gauer, Bray-Curtis and the Lance-Williams measure all are normed measure. The Mahalanobis measure is actually normed by the variance, the Gauer's measure by the range, the Bray-Curtis and the Lance-Williams by either the observations or by the sum of the observations. All these measures are related to continuous variables. For binary variables, we use either Jaccard's coefficient or the Zetkowski's coefficient. An alternative is also to use the matching proportions. The matching proportions are also used when we look at polytomous variables. Polytomous variables are variables where you have more than two categories. So the binary variables is basically a special case of the polytomous variables. Very often what happens is that a vector of observations can have all sorts of variables. It can have continuous variables, binary variables and polytomous variables all together. In such cases, we have a composite measure which is given by Gower and is referred to as Gower's composite measure. So these measures actually gives us the distance between two observations. Now when we form the clusters, these observations come together one by one, and hence in a cluster there are more than one observation. So now to find distances, we need to find not distances between observations only, but distances between the clusters. A very quick recapitulation of the cluster distances. First, we have the single linkage method, which is the distance between the two closest members in the two clusters. Then we have the composite or complete linkage method, which is the furthest distance between two members of two different classes. Thirdly, we have the group average linkage method. We take the average of all distances taken between one member from this class and another member of the other class. That is, if first class has n1 members and the second class has n2 members, then there are n1 into n2 such distances, and we take an average of all these. And finally, we have the centroid method, which is the distance between the centers of the two clusters. In this case, the center is given by the mean of that cluster. We can also have the midoid method, where we, instead of taking the mean, we can take the median. Now let us look at two new measures. The first of them is the Ward method. It is referred to as the incremental sum of squares method. The Ward's method is defined this way. For two clusters C1 and C2 with sizes n1 and n2, let x1 bar and x2 bar be the centroids. Now suppose we merge these two clusters to form C1 union C2, and then let x bar be the centroid of this merged cluster C1 union C2. The method looks at the increment in the within cluster sum of squares on merging the two clusters. So previously there were two clusters and there were two sets of within cluster sum of squares. But when you merge these two, you get a single large cluster, and obviously the within cluster sum of squares changes. The formula for Ward's method is given by D12. If you look at this formula here, you will see that the first part is xi minus x bar prime xi minus x bar, which is summed over C1 union C2. So this is the within sum of square of the merged cluster C1 union C2. Whereas the second part in the third bracket has two components. The first component is the within sum of squares of the first cluster C1, and the second one is the within sum of squares of the second cluster C2. Now when you merge these two clusters, it is obvious that the within sum of squares would increase. Remember that there would be a between sum of squares which would be decreasing, because there is no between sum of squares when you actually merge the two clusters. Hence you have all the variation within the cluster itself, and the within cluster sum of squares would be increasing. The difference between these two quantities is what the incremental sum of squares measures. Now once you have the incremental sum of square measure, you can simplify this to D12 is equal to n1 n2 by n1 plus n2 into x1 bar minus x2 bar prime into x1 bar minus x2 bar. So what you are looking at is the difference between the square difference between the two centroids, which is in this case normed by 1 by n1 plus 1 by n2. So it's the reciprocal of the observations summed up that is used as the norming factor in this case. Now this is one of the distance measures that is very commonly used, and you try to merge clusters such that you can get a minimal measure of this. The next measure that we discuss is the information measure as proposed by Shannon. Shannon's measure is primarily for non-continuous data. Here, suppose we assume that all the m variables are binary. Say either they are 0 or they are 1. Then let's define Aj as the number in the cluster C with 1 for the jth variable. The remaining, of course, would be zeros. So n minus Aj would be the number of zeros for the jth variable. Then the information content of the cluster C with n members is IC is equal to mn log n minus summation Aj log of Aj plus n minus Aj into log of n minus Aj. Now, having defined the information content of the cluster, we next find the distance between the clusters C1 and C2. Now, to do this, first we get the information content of the cluster C1, then that of cluster C2. These are respectively IC1 and IC2. And we also need to find the information content of the cluster C1 union C2, that is the merged cluster. We take the difference of the information contained in the merged cluster and the sum of the information clusters of the two individual clusters C1 and C2. This gives us a distance between the two clusters C1 and C2. Now, having defined the distances and the cluster distances, let's go back and see what we actually do in agglomerative clustering. So we decide on the type of distance between individuals first. Then we decide on the type of distance between the clusters. Then we start with n clusters having a single member each. So if there are n members, we start with n clusters. From the distance matrix, we find the minimum of the distances between the clusters and merge the corresponding clusters into a single cluster. So at the second step, we have, instead of n clusters, we have n minus 1 cluster, of which n minus 2 clusters have 1 member each and the last cluster has 2 members. And again we recalculate the distance between these clusters. Of course, we need to do it only for the newly formed clusters and keep repeating the process. So what happens is that the clusters get merged with each other as we go along, the closer clusters coming together at each step. Finally, all the clusters merge together into a single big cluster and we have our tree or the dendrogram. This is primarily the agglomerative clustering technique. Now let's look at an example. In this example, we will work with the single linkage first and the complete linkage later. In this case, we are using the same data set and we get two trees, one through the single linkage method and the other through the complete linkage. You can see that we have taken 12 distinct individuals and we have formed these two trees. There are two interesting things to look at when you look at we compare between the two trees here. One is that the trees by the two methods are slightly different. If you look very closely, you'll see that in the single linkage method, 8 clusters with 3, 11, 5 and 12, and then this 5 of individuals cluster with 4. Whereas in the complete linkage method, 8th and the 4th individual actually merge together before they merge with the remaining 4, the 3rd, the 11th, the 5th and the 12th member. So using different types of distances or using different types of cluster distances can give you slightly different clusters. One other aspect that you would notice here is the height of the dendrogram. Now, the height of the dendrogram is actually defined by the height at which each cluster merge. The height is given by the minimum distance at which they merge. If you look at the left-hand side picture, you will see that in the single linkage, the height is only somewhat beyond 60, whereas in the complete linkage, it goes much farther higher. It merges at around 120 into a single cluster. So the heights are different in the two linkage methods. But then the question arises as to which clustering methods should we use. So we need to compare between the different clustering methods. As for comparisons, there should be certain criteria. The first of this criteria is the monotonicity criteria. What is meant by monotonicity? Now, let at the kth merger, delta k be the minimum distance between the clusters. Now, this is also the height of the dendrogram at which these two clusters meet. Now, what we expect is that when we do the next step, the height would be greater than the height at the previous step. So, we should have delta k less than equal to delta k plus 1, because we have already merged certain clusters at the kth stage, and then we are merging a new element or new cluster with this merged cluster. That cluster obviously should merge at a higher level. This is what we refer to as the monotonicity. Now, most of the clustering techniques actually lead to monotonic clusters except the centroid method. In centroid method, we can sometimes have what is referred to as a reversal. That is, when we have two clusters, and when we merge the two clusters, actually the delta becomes smaller. So we can have a dendrogram which at some stage might come down a little bit at a higher level. Now, this is not very desirable, but it can happen if you have outliers in the clusters, and when you center them, when the outliers move from one to the other to the combined cluster, then probably it might bring down the height of the dendrogram. So we should prefer to have monotonicity in a cluster. The next aspect that we look at is known as the spatial property. Now, what is meant by a spatial property is that as we make more and more mergers of the cluster, the intercluster distances may show various types of characteristics. These are primarily of three types. The first is referred to as it retains its original spacing. So the clusters keep on merging with each other, but the relative distance between the clusters do not change by much. As opposed to this, we can have contracting clusters. So what is meant by contracting clusters is that as more and more merging takes place, the clusters move closer to each other, often forming a chain. So what they do is they keep coming closer and closer to each other as you keep merging the clusters. Maybe the smaller clusters actually bring two larger clusters closer between themselves. As opposed to these two, we have the dilation, which is the clusters shrink away from each other. In fact, if you look at this in astronomy, they always say that the universe is either shrinking or is dilating. So same thing can happen with clusters as well as we go on merging them. Let's look at the different types of clusters and what their spatial properties are. The space contracting clustering methods, the first of them is the single linkage method. This is an extreme case because remember, in single linkage we are combining clusters based on the nearest members of the two clusters. So they bring the two clusters closer together. The group average method and the centroid methods, these are also space contracting. On the other hand, if you are looking at space dilating methods, you have the complete linkage method, which is the other extreme, because again remember that in this case you are merging two clusters based on the two furthest observations. So actually they would be pulling away from each other. So not so extreme, but the incremental sum of squares method and the information measure of Shannon also are space dilating. So single linkage, group average, centroid methods usually are space contracting. Space dilating would be complete linkage, incremental sum of squares, and information measure. Now very quickly let us go back and think of the example. If you look at the single linkage method, since it's space contracting, therefore the height is not so high. So the clusters come together very quickly. But if you are looking at the complete linkage method, we found that the height was much higher. That is because it was space dilating and the clusters actually was pulling away from each other. So they came merged together at much higher levels. So that is something that would be reflected in the dendrogram. And you'd be expecting space contracting methods to give you smaller heights in the dendrograms, whereas the space dilating methods giving you much greater heights in the dendrograms. A few more comments. One is computational simplicity. Single and complete linkage obviously are quicker, but there is not much difference otherwise. And is these days of computational novelty, there I should feel that there is not much difference between the different linkage methods as far as computation is concerned. Stability wise, now what is meant by stability is you have errors and noises in any observation. But when you look at the clustering technique, these errors and noises are not accounted for. And hence the clustering techniques can be sensitive to outliers. So we should be very careful about outliers, because outliers can form a cluster by itself. They would be very hard to merge with other clusters, or if they merge with one or the other cluster, then they tend to pull away the centroid of the cluster, somewhat distort the whole cluster itself, and hence we should be very careful about outliers, and they actually disturb the stability of the clusters. One other thing that we should keep in mind is that when we do agglomerative hierarchical clustering, we have no provision for correcting misclassifications. What is meant by this is that we do not reallocate members from one cluster to another cluster. So if by mistake one member gets allocated to a given cluster at an early stage, it cannot go back to another cluster at a later stage. So we have a problem of reallocation. This is one of the things that we need to be careful of when you look at agglomerative hierarchical clustering. In today's module, we have discussed the hierarchical agglomerative technique. We started by recapitulating some of the distance measures that we have done in the previous modules. We have also discussed a few new distance measures between clusters, particularly the Ward's method and the Shannon method. We then briefly discussed how to form the clusters. And then what we looked at was the different properties that this clustering technique should have. So how to judge between the clusters? We can look at the monotonicity property, we have looked at the spatiality property, and we have also looked at the computational aspects of it. So broadly speaking, we have covered everything that we need to know about agglomerative clustering technique.